take a look at this pattern. 1 can be written as 1 squared. Now 1 plus 3 is 4. 4 is 2 squared. 1 plus 3 plus 5, gee, that's 9, can be written as 3 squared. Now notice that we have 2 items here and we have 2 squared. We have 3 items here, we have 3 squared. We have 1 item here, we have 1 squared. Let's take it another step. We have 4 items here. We're adding the first 4 odd numbers, you see. 1 plus 3, that's 4, and 5, 9, and 7, 16, can be written as 4 squared. Then when we add another item, we are adding the 9, and we get a sum that it turns out to be 5 squared. Well, we're wondering then if it's the case that when we add the first n odd integers, if that sum is equal to n squared. That is, the sum of the first n odd integers, which can be represented like this, 1 plus 3 plus 5, and so on, through the nth item. Now, we can show that the nth item has this form. We can use our notion that the numbers in this series are arithmetic in nature, and therefore we can generate the nth term, and the nth term is this term. Okay. So is it true that the sum of these rascals is equal to n squared? We're adding n items, and is it equal to n squared? That's what we'd like to prove. Now, we're trying to prove that this conjecture holds for an infinite number of items. And to show that, if we're taking a kind of a direct approach, we would have to sit down and show that this is true for every item that we consider. Let's see, if n is 10,000, let's show that it's true. If n is 10,001, we have to add 10,001 items and show that it's the number squared. You know, it isn't possible to prove like that, a conjecture that has this infinitude involved with it. Well, we need a method of proof that is sort of indirect. And the method of proof we're talking about in this section is mathematical induction. There are other methods, by the way, of indirect proof. I'm going to show you one here. I just very briefly, because I want you to understand that math induction falls into a family of proofs that are indirect. And another member of the family is pretty easy to show. It's the idea that if I've got a couple of numbers A and B, then we know that one of these ideas is true, that either A is equal to B, A is less than B, or A is greater than B. Now, if you have a couple of numbers A and B, and you want to show that which one of these is true, whichever one you think is true, one way to do it, because we have only 3 possibilities for an order relationship between a couple of numbers, then if we assume that this is true and then we arrive at a contradiction and show it can't happen, and then we assume that one is true and we show that it can't happen, then we have sort of by default shown that the 2 items are equal to one another. So that's an idea of indirect proof. We're not actually proving directly that A is equal to B, but we show it indirectly because there are only 3 possibilities and we take out 2 of them. All right, so that's the idea of indirect proof. Now, mathematical induction is, we talk about it in this section because math induction is often used to prove conjectures having to do with sequences and series, and that's what we're studying in this chapter. All right, math induction involves 2 steps. Here are the 2 steps. To prove that a proposition is true for n items, we need to show first that the proposition is true for n being 1 for the first item. And then, and here's the kicker, we need to show that the truth of the proposition for k items implies the truth of the proposition for k plus 1 items. That is, the truth of the kth item implies the truth of the k plus 1th item. Now, this situation, these 2 ideas together, creates a kind of a domino effect in this situation. If we show that the proposition is true for the very first item, then that kind of kickstarts the whole notion. But then when we say that the truth of the kth item implies the truth of the k plus 1th item very generally for any k and k plus 1th combination in the entire group of this infinitude of propositions, then isn't it true that the truth of the first item implies the truth of the second item? And the truth of the second item implies the truth of the third. And the truth of the third implies the truth of the fourth, and so forth. Why, with this idea that the truth of the kth item implies the truth of the k plus 1th item. Okay, so here's what we're going to do in our problem. We know that the sum of one item is 1 squared. The sum of 2 items is 2 squared. The sum of 3 items is 3 squared. Now, we've shown that the proposition is true when n is 1. Okay. Then we show that if the sum of k items is equal to k squared, if this conjecture implies that the sum of k plus 1 items is equal to k plus 1 squared, then we conclude that the sum of n items generally is equal to n squared. Okay, it's this implication that is so very important in mathematical induction. Now, the representation of the k plus 1th item sometimes is an imposing matter in using math induction. And let's just talk about that briefly here with a couple of examples. If s subscript k is 2k squared, then s subscript k plus 1 can be generated. The expression for that can be generated in much the same way that we use functions. The k plus 1th item, if that's the kth item, can be represented as 2 times k plus 1 squared. You see, just replace k with k plus 1. You see, and here also, now we could clean that up a little bit, but we're not going to bother to do that. I just want to show the quick representation here. If this is the kth item, you see s sub k is this, then s sub k plus 1 means replace all the k's with k plus 1, so it would be k plus 1 over k plus 1 plus 2. And again, we could clean this up a little bit, but that's the general idea. All right, let's get back to our problem. We want to prove that the sum of n items, which is represented by this group of items being added, is equal to generally n squared. So the sum of n items is equal to n squared. Now, by math induction, here's what we do. We prove that s subscript 1 is true. For n equals 1, the sum of 1 items is 1, and we can represent 1 as 1 squared. So that shows that that's true. Then we assume the validity of the kth item. That is, we assume the truth of s subscript k is equal to the sum of these k items is equal to k squared. Now, does this idea imply the truth of the sum of k plus 1 items is equal to k plus 1 squared? Now notice the idea that if this is s subscript k, then s subscript k plus 1 means replace the k with k plus 1 and we have k plus 1 squared. Okay, so that's the idea. Now, to show this implication, we have to show that s subscript k plus 1 is equal to k plus 1 squared. But how do we represent s subscript k plus 1? Well, let's see. It's the sum of k plus 1 items, but we know that the sum of k items is this. And then we add one more item and we have the sum of k plus 1 items. Well, what's the next item in this group? We have 1 and 3 and 5 and 7 and 9 and so forth, and we're talking about odd numbers and they differ from one another by 2. So if we just take this 2k minus 1 and add 2, we'll have the next item. So 2k minus 1 plus 2 would be 2k plus 1. So 2k plus 1. Now we know we're assuming the validity of this rascal right here. We're assuming the truth that adding all of those items, that s subscript k is equal to k squared. So s subscript k is k squared. So we have k squared plus 2k plus 1. And factoring this, we get k plus 1 squared. Aha! So the truth of this implies the truth of this. That is, the sum of k plus 1 items is k plus 1 squared. And now by math induction, we have proven our conjecture. Let's use math induction to prove this conjecture. It says that the sum of n items given by 1 plus 2 plus 3 plus 4 and so on through the nth item is equal to the expression n times n plus 1 over 2. Is that true? Well, let's see what this means. If we're talking about adding 4 items, 1 plus 2 plus 3 plus 4, that would be 4 and 3, 7 and 2, 9 and 1, 10. So that sum would be 10. Does it meet the form over here if n is 4? Well, this would be 4 times 4 plus 1 over 2. 4 times 5 is 20, 20 over 2, 10. So it certainly works when n is 4. Now, by math induction, here's what we need to do. We need to show that the conjecture is true when n is 1. So when we're adding just one item, the sum of one item would be 1. Now, does it meet the form that we have over there? Well, that would be 1 times 1 plus 1 over 2. Well, this is 2 over 2 or 1, so it certainly works in that case. Now, we then assume the truth that the sum of k items meets the pattern that we talk about, that we have in the conjecture. But does that imply the truth for the k plus 1th item? That is it therefore the truth that the sum of k plus 1 items given by all of these plus the next item, you see, equal to this expression for the k plus 1th item? Now, here's where we have to think about how to write this and where this comes from. This is the k plus 1th expression, and just replace this k with k plus 1, replace that with k plus 1, you see, and we get this. Okay, so that's the idea. Now, in order to show this, the strategy generally is to write this and show that, and then make a replacement, refer back to something that you made in this assumption. All right, and then we want to lead to this expression. So that's the idea. So we start with the sum of k plus 1 terms would be 1 plus and so on all the way to adding the k plus 1th item. All right, and then we utilize this information and then try to show that. All right, here's what we're doing. We take s sub k, all right, here's s sub k. Now s sub k plus 1 means just tack on the k plus 1th item. That's what this is. All right, now, here's where we jumpstart the whole thing. We take this part of it right here, and we replace with that. You see that expression. Okay, so that's what comes down to right here and replaces this. And now we still have the k plus 1th item being added. Now we want to manipulate this expression into the form that we want it. Then that form was k plus 1 times k plus 2 over 2. Okay, let's see if we can do that. We see that in these two terms, k plus 1 is a common factor. So we pull out k plus 1 as a common factor. When we pull k plus 1 out of this term, we're left with k over 2. When we pull k plus 1 out of this term, we're left with 1. Now, what about this? What's this? Well, let's see. We have a fraction here. We need common denominators. 1 can be thought of as 2 over 2. So when we write 1 as 2 over 2, we have k plus 2 over the common denominator 2. So this becomes that. And now we can rearrange factors a little bit and write this as k plus 1 times k plus 2 over 2, which is what we need to do. And our proof is complete. Here's one that involves an inequality, and the strategy for inequalities is a little different. This is one of the nuances involved in using math induction. All right, here's the conjecture. It is this, that n factorial is greater than 2 to the n power for all values of n greater than or equal to 4. Greater than or equal to 4. The conjecture here is starting at a point other than 1. Our other conjectures started with 1. It's kind of like we have a counting mechanism and the counting starts at 1. Well, the first item in this conjecture is 4. And then we go from there. We go 4, 5, 6, 7, 8, and so forth for the value of n. So here's what we have to do. When we use math induction, we have to start with the first item in the conjecture, and then we go to the second part. All right, for the first item, for n equals 4, we want to show that 4 factorial is greater than 2 to the 4th power, and all we do is evaluate on each side of the inequality. 4 factorial is 24, 2 to the 4th power is 16. 24 is certainly greater than 16. So we have shown the conjecture true for the first item in this group of items. All right, now we want to assume the truth of the kth item, that is that k factorial is greater than 2 to the k power. And we want to show, or we're asking ourselves, if that does that imply the truth for the k plus 1th item? And the k plus 1th item is replace k with k plus 1, replace k with k plus 1. You see, does this imply the truth of that? Now the strategy here in dealing with inequalities is this, and I want to contrast it with the previous strategy. In the previous problem and the one before that, we had an expression, just an expression that we were manipulating. And we utilize information from the assumed truth situation. All right, now here we're dealing with an inequality, which means that we have two sides of this rascal. So we start with this assumption, and then we begin to manipulate by sort of attacking one side of the inequality or the other and making it look like this. And then we attempt to deal with the other side. Here's what I'm talking about. We're going to start with this and then decide what we need to do. And I chose to pick on the left side. What do we need to do? What additional factor do we need on the left side of this inequality to cause this to happen? You see, think about that for a moment. We're going to move over here. So we start with the assumption that k factorial is greater than 2 to the k power. And we want to show that this implies the truth of for the k plus 1th item. Okay, now to begin the manipulative process, I recognize that if I introduce a new factor here, that is a k plus 1 factor, that this will become k plus 1 factorial. Okay, so I'm going to do that. So I'm just going to multiply on both sides of the inequality by k plus 1. Now I know I'm multiplying by a positive value here because our original assumption was that n was greater than or equal to 4. So this k then, this k value is certainly a positive value. Okay, so k factorial times k plus 1 is k plus 1 factorial. All right, now I have made this side of the inequality look like the item that I want it to look like. But this one doesn't look anything like what I want it to look like. So now I have to begin some manipulation over here. All right, and I do that like this. I'm going to take an aspect of this expression. I'm just going to take k plus 1 and I'm going to set it greater than 2. Now I'm choosing 2 for a particular reason. Let's understand what I'm after here. Let me back up over here and let's just refer back. I want to show that this is greater than that. Now I have this on the left side of an inequality over there. Now I want to pick on the notion that I want that rascal to be greater than 2 to the k plus 1. So over here I want somehow to show that we have greater than 2 to the k plus 1. I want to show that somehow. So I need multiple factors of 2 over here. And that's why I'm taking an aspect of this side and I'm setting it greater than 2. You see, in order to get to that point, the point where I can say this. Okay, now I can say this certainly is true because the n in the conjecture was that n is greater than or equal to 4. So k is greater than or equal to 4, and therefore greater than or equal to 4 plus 1 is certainly greater than 2. So that has to be true. And now I'm noticing, gee, I need a bunch of factors over here. You see, I need a lot more factors over here to get to that kind of form. That's what I'm after. And so I'll multiply on both sides by 2 to the k power. So I'm multiplying this by 2 to the k. I'm multiplying over here by 2 to the k. And lo and behold, over here I have 2 to the k plus 1, which is exactly what I'm after. And on the left I have 2 to the k times k plus 1, which is this. You see, and now I can use the transitive property. If this is greater than that and that is greater than this, I can conclude that this is greater than that. You see, and that's what we were compelled to do in showing the second part of the proof by math induction. Suppose we want to show that 3 is a factor of polynomials in this form where n is any positive integer. Now, to show that, we have to show that, first of all, that when n is 1, that 3 is a factor of the polynomial when n is replaced by 1. Now, let's see. P sub 1, the polynomial when n is 1, would be 1 cubed, comes from up here, plus 3 times 1 squared, plus 2 times 1. Well, let's see. 1 cubed is 1. 1 squared is 1, so this is 3. Plus 1 would be 4, and this is 2. 4 and 2, 6. So p sub 1 is 6, and 3 is certainly a factor of 6. So it works for n equals 1. Now we have to show that the assumed truth of the kth item implies the truth of the k plus 1th item. That is, we assume that 3 is a factor of p sub k, which has this form. And we want to show that 3 is a factor of p sub k plus 1. All right, we begin this way. We start by writing the p sub k item. And now, the p sub k plus 1 item is an item that comes from replacing these k's with k plus 1s. You see, and once we've expanded in that way, we need to show that 3 is a factor of that expression. Well, it gets a little thick with algebra here. K is replaced with k plus 1 here and here and here, and then we begin to expand. Well, cubing k plus 1, we get k cubed plus 3k squared plus 3k plus 1. And then squaring k plus 1, we get k squared plus 2k plus 1. And in the next step, we'll multiply by 3. But out here, we have 2 times k plus 1 is 2k plus 2. All right, multiplying here, we get, let's see, I brought down these terms, and now 3 times k squared, 3k squared, 3 times 2k, 6k, 3 times 1, 3. Now we have a string of a whole bunch of terms, and we want to just bring together the like terms. K cubed, only cubed term in the bunch. We have a k squared term here and another one here. 3k squared, that's 6k squared. 3k and 6k is 9k, plus 2k is 11k. And then the constants, 1 and 3, 4 and 2, 6. Now we'd like to show that 3 is a factor of this. Now the real trick in all of these kinds of problems is to utilize the assumed information. That is, utilize the information here that 3 is a factor of this. Now if 3 is a factor of that, then we can show that 3 is a factor of this. Because here's what we do. We're going to separate this polynomial so that we have a part that looks like that. You see, I'm going to just rewrite this and pull out those factors or those terms. I'm going to write k cubed plus, I'm just copying that down, k cubed plus 3k squared plus 2k. Now what's left over? Well, I've already written the k cubed. 3k squared, what's after that? And I'm going to put this in parentheses just for emphasis here. I really don't have to do this, but just for emphasis I'm doing this. All right, I'm pulling like 3k squared out of here. What's left? Another 3k squared. I pull 2k out of this 11k and I'm left with a 9k. You see, and then I have, now I'm not factoring here. I'm just separating 11k into 2k plus 9k. You see, it's just a separation of terms here. And then I have a 6 up here, so I need to bring that down. All right, now, by making that separation and going with the assumption that 3 is a factor of this, which is what we assumed from above, we know that if 3 is a factor here, then we can factor this into 3 times something, if 3 is a factor of it. And now we have plus 3k squared plus 9k plus 6. Oh, I see 3 factors in all of these terms. So I can factor this business into 3 times something plus, yank the 3 out of this and we have k squared. Yank 3 out of this and we have 3k. Yank 3 out of this and we have 2. So I have a form that is factored in such a way that 3 is a factor of this business up here, the p sub k plus 1. So 3 is indeed a factor of p sub k plus 1, and we have proven the conjecture.